But however, if we have more frequencies, then for example, let's say uh, something like this, yeah, then we may have we can maybe differentiate this into two or triple frequency, yeah. For example, let's say this is 10 hertz, maybe this is 20, etc. This is frequency in hertz. So, but in more complex signal, yeah, in more complex signal, for example, that the signal is random, more random, let's say EMG signal or ECG, then you will have a more of in the frequency domain, you will have more continuous continuous uh, signal in the frequency domain. So, what the meaning of when we want to do filtering is that we filter part of that frequency. Yeah. So, for example, we have triple frequency signal. For example, here we have uh, signal with low frequency, and then we have here signal with maybe a bit higher frequency, and then we have another signal with very much higher frequency. Okay, so when we pass this into a filter, let's say a low pass filter, for example, then what happens is that the signal will be cancelled out. The signal will also be cancelled out, and the signal will be passed through. Then at the end of the block diagram, what we will have is a signal with only the low frequency part, yeah? Only the low frequency part. So this is one example of the filter, which is a low pass filter. So based on the frequency that a filter pass, we can divide the filter into several types. Yeah? The first one will be the low pass filter, yeah, which maybe many of us already know, and it has been used by in many different circuits. Yeah. Most of the biomedical circuits use low pass filter because most of biomedical signals are low pass, are low frequency, yeah, maybe maximum 100 hertz, except for the brain signal. Brain signal is maybe one of the biomedical signal that has very high frequency in the range of kilohertz. So we have here low pass filter, then we have the high pass filter, and then we have the band pass filter. Okay, so are there more? Any other signal? Yes, we have. The other part is the what we call also as the band reject filter, yeah, or band notch filter. Band reject filter. So in low pass filter, as the name implies, it pass frequency at low frequency. So what we have is something like this, where the cutoff frequency is where it stops the frequency higher than that cutoff frequency. So here, what this is what we call as the pass band. Yeah, so this is amplification. The y-axis is amplification, while the x-axis is the frequency. So the low frequency here, where the signal in lower than frequency cutoff is pass, then it is called as the passband frequency. While after the cutoff frequency, where the signal is being stopped, we call it as stop band frequency. Okay. So in low pass frequency, the stop band frequency is at higher region, passband is at low region. When we have a high pass filter, it is the other way around. So in high pass filter, so this is F, y-axis is the amplification factor. Then the signal at the high frequency will be passed. The signal at high frequency will be passed, and on the signal on the lower frequency will be stopped. So this is the stop band in high pass frequency, and this is the pass band. And the frequency where it cuts, yeah, this signal is called as similarly as cutoff frequency. But only for high pass filter, it is frequency that higher than the cutoff frequency will be passed by the instrument, and signal with lower than cutoff frequency will be stopped. Or with band pass filter, on the other hand, is we have a signal, yeah, we have a characteristic or transfer function where it cuts signal higher or lower than the two cutoff frequency. In band pass filter, we have two cutoff frequency, yeah, at low frequency region and at high frequency region. So this is again the amplification. So we have frequency cutoff 1 and we have frequency cutoff 2. So the passband frequency will be this one, the middle part, yeah, where signal is passed by the filter. This is the passband frequency. And the stopband frequency are in the two regions. First one is below the FC1, below the frequency cutoff 1, and the second one is above the frequency cutoff 2. This is stopband. Yes. Then finally, with band reject filter, it is the opposite of band pass filter. So, or we call it band notch filter, yeah? Band notch filter. In band reject filter, yeah, what we have is it is similarly also expressed or shown with two cutoff frequency, but so FC there is a FC1 and there is also FC2. But now it is the opposite of band pass filter. Frequency below the FC1 is being passed, while in band pass filter it is being stopped, right? So here the middle part between FC1 and FC2 is the stopped band region, yeah, where signal will be stopped or will be rejected. That's why it is called band reject filter. Where signal above the FC2 will be passed, yeah, so this is passband 2, let's say like that, passband 2, while also the signal below frequency cutoff 1 will also be passed. Yeah, passband 1. Okay, and based on the component, whether we yeah, whether we express or whether we build that filter using passive component or amplification with active components, then filters can also be divided into two types, yeah, either as a passive filter or active filter. So let's say this. So based on the component which we use to develop that filter, so we can divide component into active and passive. Or to passive first, and then active filter. So passive filter usually use passive components, as the name implies, either resistor or capacitance or inductance. So for example, for low pass, yeah, low pass filter, this can be implemented using either RC component, RC, which we call it as RC low pass filter, or RL component, yeah, a resistor and inductor, RL pass filter, or all the three passive component, RLC component, resistor, inductor, and capacitive component. Active filter You already know, yeah, maybe some of you last week already did some example on it using most famous component is using operational amplifier, but it can also be implemented using transistor. Okay. Okay. Any questions so far? Yeah, regarding no question. I think it's everyone already know about this. Most of you, yeah, in electrical circuit as well as in electronics, this has been reviewed many times. So now let's try to uh, discuss the low pass filter part. Low pass filter part. Okay. So the low pass filter part is usually an passive low pass filter. Passive low pass filter. So ideally, as what I have drawn in the previous slide, yeah, or in the previous board, that in passive low pass filter, what we have is the ideal characteristics will be everything above the cutoff filter will be cut. Okay, so this is an ideal low pass filter characteristics. So this is frequency and this is the amplification. Okay, but this is the ideal case. In reality, it is not so. So for example, if we use first order active circuit, so first order passive low pass filter, what we will have instead is something like this. Okay, like this, and it will be cut like this. So at the cutoff filter, yeah, the the amplification will be how much? Anyone knows? Yeah, Teddy, how much? The amplification during the cutoff filter. Yeah. In ideal, sorry, in actual first order low pass filter. Yeah, the red one here, first order passive low pass filter. What will be the value here? The amplification. Do you remember? Diana? Here, the amplification at the cutoff frequency, what is it? By definition. Any idea, Diana? Jeremy?
3 dB.
3 dB, yeah. Or in
0.7.
in numbers, 3 dB is in the decibel unit, but is normal number, ratio number, how much is this? Yeah, this is correct. How much is this?
0.7071.
Yeah, 0.7071. Or in rational number, this is 1 over square root of 2. Okay, so that is the ideality. Then it will decay by it will decrease by a magnitude of minus 20 dB per decade. Okay, so minus 20 dB means per decade means per 10 times of the frequency. Yeah, so 10 at 10 FC, for example, it will decay by 0.0701. Okay, at 100 times of FC, so it's already 2 decade, right? then it will decrease by minus 40 decibel or 0.007071, something like that. Okay. Okay, so where does this come from? Later we will derive. Yeah? So this is first order passive filter, and the circuit used to implement this is just a simple RC circuit where the input voltage is connected to the resistor and the output voltage is connected to the capacitor. So from here we know that V out equals to XC divided by R plus XC, right? It is basically a voltage divider. Only now we have to use reactance instead of just resistor. So times V in, yeah, times V in. So then the magnitude of V out divided by V in equals to magnitude of XC divided by the magnitude of R plus XC, or this equals to XC divided by square root of R square plus XC square, right? So here the XC itself equals to 1 over, the magnitude of XC is 1 over omega C. Okay, XC itself equals to 1 over J omega C, yeah, 1 over J omega C, or minus J divided by omega C. So here the magnitude will be this 1 over omega C. Only it has a negative 90-degree phase lagging, yeah, uh, from the voltage. Okay. Clear? So let's do again. This is V out. So V out is divided by V in equals to R, sorry, XC, yeah, divided by square root of R square plus XC square. Okay, so this, if we replace XC with omega C, so this will be 1 over omega C, okay, divided by square root of R square plus 1 over omega C square. Omega square C square. Please correct me if I'm wrong. Yeah? So from here, we know that what is the frequency? Yeah? What is the cutoff frequency? Yeah? The cutoff frequency happens when at cutoff frequency is V out divided by V in equals to 1 over square root of 2. Okay, this is 3 decibel. So it means, hence, then if we put this into the upper equation here, so this 1 over square root of 2 equals to 1 over omega C divided by square root of R square plus 1 over omega square C square. Yeah, and then if we square both sides, then this becomes half. This becomes 1 over omega square C square divided by square root of R square. Oh, sorry, the square root now gone. Okay, so this become R square plus 1 over omega square C square. Okay, if we multiply both numerator and denominator with omega square C square, yeah, this is also omega square C square. So this will be equals to 1 over R square omega square C square plus 1. Okay, so from here it means that 2 will be equals to omega RC square, yeah, plus 1. Okay, so omega RC square equals to 1. Yeah, so it means that omega RC equals to 1 plus minus 1. Okay, but we choose the positive value only, 1. So here omega equals to 1 over RC. Yeah, this is one equation. Then if we express omega equals to 2 pi f c, cutoff frequency, omega, this is the cutoff frequency, because this is when V out is 1 over half to 1 over square root of 2 multiplied by V in. So here, then it means omega c, oh sorry, fc, yeah, fc will be equals to 1 over 2 pi rc. So here, if the cutoff frequency is defined by the, and then you are asked to design a low pass frequency, yeah, with fc with fc is known, fc is set by the design, then you can determine the value of the r and c accordingly. Okay, so let's have a try on this. Any questions so far regarding the derivation of the cutoff frequency? No question, yeah? And the V out divided by V in is this value. Yeah? This is the transfer function. Okay. Of course, can you simplify this? Yes, you can simplify this further. If you would like to simplify this further, so this will be equals to, so V out divided by V in. If you multiply both the numerator and denominator with omega c, so this will be equal 1, and then square root of omega square r square c square plus 1. So this is the transfer function, the simplified transfer function of a low pass filter. Understand so far? No question? No?
No,
Ready for quiz? Immediately. Quiz or not?
I don't know.
Okay, just exercise. Yeah. So if I save this and then we clear, let's have some exercise. Let's say here we have first is analytical part. Yeah. Oh, I could. Yeah, this is for undoing. Clear on drawing. A circuit here, a low pass filter. So number one, let's let ask Nasser to do it. Nasser, are you ready? This is 1 kilo ohm of resistor, and this is 0.1 microfarad. So Nasser question will be very simple. Determine the cutoff frequency. Then the same circuit. Who would like to volunteer? Elnora. Okay. What is the V out when frequency is 2 kilohertz? Okay, Elnora. Okay. Okay, I will pause the recording.